We've talked about several types of energy, and if you haven't watched the video on Hooke's law, you need to watch that first. But now we can talk about energy that can be stored in a spring. So we have a spring on here, and if we started pulling on this spring, clearly there would be some elastic potential energy in the spring, because I could release it and it would snap back. So there's clearly going to be some potential energy in the spring, and some of it's going to depend on what the elasticity constant is of the spring, and of course it's also going to determine on how far you're going to stretch the spring. So the equation for elastic potential energy, we've had a lot of different equations for different forms of energy. Here's another one. 1/2 K with the elasticity constant times the displacement squared. So now if you remember, K is, the way you calculate K is the force over the displacement that force will stretch it. So sometimes you think, well, maybe I could put F over D in for my K and then cancel out a D. But you can't do that unless these D's, this D and this D, are the same displacement. So if they are, then you could do that. For instance, let's look at this first problem where we're going to try to do a couple problems where we're going to calculate out our elastic potential energy on a spring. So in this first problem, you have a 10 Newton force stretches a spring 30 centimeters. So that is the force, and that's how far it stretches it. What is the elastic potential energy? Well, our equation for elastic potential energy is 1/2 K D squared. Now in this case, the force that's stretching it is only stretching it 30 centimeters, and I want to know what the entire elastic potential energy is. So I could do 1/2 times the force, which is 10, over the displacement, which is 30. That could be my K value, and that's actually, I'm trying to figure out what's the elastic potential energy at that displacement. So times D squared, and one of my D's would cancel out, and I could have 1/2 times the force times the displacement. I can only do that in this example where I'm trying to figure out the elastic potential energy at the displacement that the force is stretching it. I mean, if we grab onto the weight and we pull it down further, okay, then you're going to have a bigger displacement, and you're going to have more elastic potential energy, so you wouldn't be able to do that. So right here in this problem, we could do equals 1/2 times the force, which is 10, times the displacement, which is not 30 centimeters, it's 0.3 meters. Okay? So 10 times 0.3, of course, is 3, and half of that is 1.5 joules of energy is how much elastic potential energy would be in this problem. So let's go ahead and take this exact same spring. Okay, so let's figure out what was the K value. Well, it was force 10 divided by the displacement 0.3, which would equal basically 33.3 newtons per meter. That was my K constant. So I want to use that, because in my next problem I'm going to use the exact same spring. However, we're going to stretch it 50 centimeters. So I'm going to write down my K value. If you remember, my K for this spring was 33.3 Newton per meter. I want to know if the same spring is used, which means I'm going to have this exact same K value, and we stretch it 50 centimeters, what is the elastic potential energy? So elastic potential energy equals 1/2 K D squared. So that would equal 1/2. My K value is 33.3. And the displacement that we stretch it is 0.5 meters. And you always got to remember that is squared. So we take 0.5 squared times 33.3 times 0.5, and we get around 4.2 joules of energy. because we stretched it further. So this is how we use the equation for elastic potential energy. And we need to figure out a K value for the spring first, and then take it times the displacement squared, and then take 1/2 of that. Before we go on, I want to just kind of throw out one more thing here. When you put a mass on a pendulum, we talked about a mass on a pendulum before, and we talked about the period of the pendulum, which is how long it takes to swing over here and then back. And if you remember, the equation for the period of a pendulum was 2 pi times the square root of L over G. So what about a spring? I take a spring and I put some mass on here and I drop it. Well, then this thing is going to oscillate. It's going to go oscillate back and forth also. So what would the period be of this thing oscillating back and forth? Well, it's very similar. It's still T equals 2 pi times the square root of. Now, what does this thing depend on? Well, this one, a spring, actually is going to depend on the mass. Remember, the period of a pendulum didn't depend on the mass at all. But this one is going to depend on the mass of this. So instead of L, which is the only thing the pendulum depended on, for the period of the mass, for the period of the spring pendulum, if you will, we're going to have the mass over, well, up here, what did we have? We had it over gravity. Gravity was a constant that didn't change for this particular pendulum. So what do we have for a constant that's not going to change for this particular spring? We actually have the K constant. So these are very similar. This is the period for a swinging pendulum, and this is the period for an oscillating spring. 2 pi times the square root of m over k. You might have recognized that from one of the labs we did at the very beginning of the year. So I don't have a problem to do for that, but it'd be pretty easy to do if I gave you the mass of something we're going to put on a spring and you knew the spring constant. You could easily figure out how long it takes for it to oscillate one time, would be the period.